Space missions typically follow a safe pattern. You pick a target, design the spacecraft, and send it straight there. That's how we've studied Mars, Saturn, Jupiter, and even comets like Halley and 67P with Rosetta. The plan is built around certainty, but we are building a spacecraft designed to ambush a cosmic stranger. It will wait in deep space, perfectly still, until the next mysterious object like Oumuamua suddenly appears. And when it does, this mission will strike. This is the Comet Interceptor. Comet Interceptor is about embracing the unknown. The European Space Agency, in partnership with the Japanese Aerospace Exploration Agency, is building a spacecraft whose target hasn't even been discovered yet. In 2029, it will ride into space alongside another mission, Ariel, and then park itself at a special balancing point about 930,000 miles away from Earth, called L2. That is the same spot where the James Webb Space Telescope operates. From there, Comet Interceptor will simply wait, not for weeks, not for months, potentially for years. Its prey could be a pristine comet, making its very first journey into the inner solar system, carrying untouched material from 4.6 billion years ago. Or it could be something far rarer, an interstellar object like Oumuamua or Borisov, born around another star and passing through our neighborhood by chance. That's the radical idea. Instead of racing after something already known, we build the spacecraft in advance, send it to deep space, and let it lie in wait. Because when the next cosmic visitor arrives, the clock will be ticking, and we'll only get one chance. There's a key design twist in this space mission. It's not one spacecraft, it's three. A main craft called Spacecraft A and two probes, B1 and B2. Together, they'll perform a kind of 3D flyby. Each takes a different vantage point. So instead of a flat snapshot, we'll map a comet's activity in 3 dimensions. How gas vents, how dust streams, and how solar winds shape its tail. No mission has done this before. The comet we've studied so far, Halley, Tempel 1, and 67P, have circled the sun many times. Their surfaces are scarred, their chemistry altered. They're fascinating, yes, but they're not fresh. Scientists want the raw ingredients, the unprocessed building blocks of the solar system. A dynamically new comet falling towards the sun for the very first time could carry ices and organic preservatives for billions of years. And then there's the long shot, an interstellar visitor. Oumuamua was spotted in 2017, but it was already leaving by the time we realized what it was. Borisov showed up in 2019, but again, it came and went too fast. No spacecraft could be launched in time. Comet Interceptor changes that equation. If one object comes in this time, we'll already be there, engines primed. When astronomers spot a suitable comet, ideally the one that is new to the inner solar system, the spacecraft springs into action. The whole assembly maneuvers onto an intercept path, and in the final approach, the probes split off. Spacecraft A will hang back, about 620 miles from the nucleus. Probe B1, built by the Japan Aerospace Exploration Agency, will dive to about 530 miles. Probe B2 from the European Space Agency will go even closer, around 250 miles. Those distances aren't set in stone though. They'll adjust depending on how fast and how active the comet is, but the idea is clear: 3 perspective, 1 fleeting encounter. Each spacecraft also carries different instruments. Spacecraft A has a high-resolution camera, infrared imagers, and analyzers that can sniff out the gases in the coma. Probe B1 and B2 carry wide-angle cameras, spectrometers, plasma detectors, and dust analyzers. Together, they'll reveal the shape of the nucleus, the chemistry of its ices, the dynamics of its coma, and how it interacts with the solar wind. It will be a flyby, not an orbit. The relative speed could be anywhere from 22,000 to 156,000 miles per hour. The closest approach might last only minutes, but those minutes will be packed with more discovery than decades of ground-based observation. Putting this off isn't easy. For starters, spotting pristine comets early enough is tough. They're faint, barely visible until they get close to the sun. That means the mission may have only months of warning to maneuver into position. Then there's speed. At tens of thousands of miles per hour, a comet is a bullet in space. Instruments have to capture data fast, thousands of images in spectra in seconds, while also surviving a storm of dust and gas. Even small particles hitting at those speeds could damage or destroy sensitive sensors. And because the probes will split up, they won't be able to back each other up. If one gets too battered, the data stream could be cut. Engineers have built-in shields and redundancies, but the risks are real. Finally, there's the biggest uncertainty of all. Will the right comet even appear? The spacecraft could end up waiting years for a suitable target, but that's the gamble. This is a mission built for patience and for payoff. If it works, Comet Interceptor could unlock secrets we've never been able to touch. A first-time comet might show us exactly what the solar system's original building blocks looked like. Not baked, not altered, but pristine. We could trace what kinds of ices were present at birth, what organics formed into the cold, and how these materials may have seeded young planets like Earth with water and ingredients for life. Even more exciting, if the mission catches an interstellar object, we could finally compare our system's chemistry to that of another. Do other stars produce the same ices, the same organics, the same dust? Or is our recipe unique? Even a whiff of gas or dust particle from another star system would give us a glimpse of planetary formation beyond our sun. And because 3 spacecrafts will be flying in formation, we'll build the first real 3D model of a comet's coma and tail, how dust and gas flows, how jets erupt, how solar winds sculpt its structure. That sort of dataset could reshape models for decades. Comet Interceptor was selected by the European Space Agency in 2019 as its very first F-class or fast mission with linear budget, tight schedule, but high ambition. It was formally adopted in 2022, and right now, teams across Europe and Japan are building and testing the instruments. Launch is scheduled for 2029 from Europe's spaceport in French Guiana. After that, the spacecraft goes to L2 and waits. On Earth, surveys keep watching. The Rubin Observatory, set to begin full preparations later this decade, will be a game changer, capable of spotting faint, fast-moving objects that older telescopes might miss. Once the right comet or interstellar visitor is flagged, Comet Interceptor will plot its course and make the chase. The flyby could happen a few years after the launch, or much later. That's the gamble. But when the moment comes, it will be one of the highest stake ambushes in space history. Comet Interceptor is a cosmic lottery ticket. The odds are uncertain, the wait could be long, and the risks are real. But the prize, the chance to touch something untouched since the dawn of the solar system, or to meet a traveler from another sun, is worth every gamble. Because this time, when the next stranger races past our skies, humanity won't just wave as it leaves, we'll finally chase it down. This excites me, and I hope it excites you as well. Let me know what you think in the comments below. And as always, thanks for watching.